All right, let's get started. So a lot of stuff to cover today. If you didn't realize, I held the last class back for like 8 minutes, and I don't think I can do that with you guys because there's a class after me in here. So hopefully we can get through everything in the required time. So actually, you know what? I spent like 3 minutes at the beginning of class last recitation just talking about like the logistics for the exam. I'm not going to do that here. So what you're going to expect then is you're going to expect to see like an email from Professor McGrath either today or like tomorrow that talks about the logistics of the exam, like where it is. He's going to give you practice problems. He's going to give you all the details about the review sessions and extra office hours that we're going to be holding going up to the exam. So look out for that email then. So we're not going to talk about it here, okay? Does anyone just have any questions before the exam, like about the exam? Like I can answer them now. Yeah.
How much focus is there going to be on like ODEs?
I think there'll be like one question. So you do need to know how to solve an ODE. So it'll either be one of the like the physicsy type ones, it's fair game, or it could literally just be here's an ODE and solve it, like a first order ODE. So essentially, if you like go through the homeworks, that should cover pretty much anything that's fair game for the ODEs. So what's actually going to happen is one of the review sessions is going to be we're going to go over all of the recitation homeworks, and one of the review sessions is we're going to go over the regular homeworks, right? So that way, like all your bases should be covered if you like go to those. So, all right, let's jump in then to what I have today. All right, so the goal for today is we're going to go from 4.3 all the way through 4.6. Whether that's doable or not, we'll see. And let's start with 4.3, which are subspaces, right? So informally, what should I think about when I think about a subspace? So last week in this class, I opened the can of worms that were vector spaces. I think in this section, I actually did the 10 axioms of a vector space, which I'm pretty sure you don't need to know you don't need to memorize. Essentially, just put it this way: for the 10 axioms of a vector space, if something feels wrong, it's probably wrong. So that's probably good enough. Let's talk about subspaces. So informally, what is a subspace? You can think of subspace as a smaller vector space inside a bigger vector space. All right, and so VS is how I'm going to abbreviate vector space to save words, but that's essentially what it is. What's the formal definition? All right, is the following. Let big S be a non-empty subset of a vector space big V if S is a vector space under the same addition and scalar multiplication as in V, then S is a subspace of V. Okay, so that just means I have this big vector space, I have some addition operation defined on it, I have some scalar multiplication operation defined on it, and if the smaller subset has the same addition and scalar multiplication, and it's a vector space, then it's considered a subspace of V. So let's go over some examples then. All right, so how do I find subspaces of a vector space? Or how do I show that something is a subspace? So in general, we show that something is a subspace by one, showing that it's closed under addition, and two, showing that it's closed under scalar multiplication. All right? And I'm going to add this one in. This is an optional third one, but it's really helpful in showing that something is not a vector space. Show that the zero vector is in S. All right, and instead of writing in, let's put the element symbol right there. Okay, so if you show it's closed under addition and closed under scalar multiplication, you're done. That's all you really have to do. If you want to show that the zero vector is in there, we're not going to penalize you for it. It's a really good check to see if it's not a subspace. Okay, So let's see. So for example 1, take a look at the following. Let's take a look at skew symmetric matrices in MNR. Okay, so are you guys okay with this notation of MNR? Right, so it's n by n real matrices. Okay, so skew symmetric matrices in MNR. So let's talk about then a really nice way to do these types of problems is to convert whatever wording you have into set notation. So let's talk about the set notation here, and it's going to be the following. So here I'm going to define what a general element is of the set. All right, so I'm going to let S be the set, and then let's say I have A. Right, this is the general element. That's what elt means. All right, elt is element. So A is just a random matrix, right, in MNR. Okay, and then I have to satisfy some condition. All right, and so on the right-hand side of these dots, or sometimes it'll be like a straight line, here's going to be the condition that these matrices A, right, that my general element has to satisfy. Okay? So if we're talking about skew symmetric matrices in MNR, what is then the condition for a matrix to be skew symmetric? Yeah, exactly. So we want A to equal negative A transpose. Okay? Any questions? All right, so how do we read this? We read this, the set S is some matrix in MNR where it's skew symmetric, so A is equal to A, negative A transpose. All right, so now we want to show that one, this is closed under addition. All right, so how do we show it's closed under addition? Well, what do we want to show? We want to show that, okay, so closed under addition, so got a little bit ahead of myself. We're going to take two general elements, all right? So this is a general element, and that's a general element, all right? We're going to take two general elements in my set S. So what this means is that A is going to be a matrix that satisfies the skew symmetric condition, and B is also going to be a matrix that satisfies the same condition. So now I want to show that A plus B, all right, the sum of these two matrices satisfies the condition of being skew symmetric. All right? So A plus B is now my new matrix, and now I want to show that that is equal to negative A plus B transpose. So what I did was I essentially plugged A plus B into my condition. Okay? So how do I show this? We do it the following. So I can either start on the left and go to the right-hand side, or I can start from the right-hand side and I go left. I'm going to start with the right-hand side. So I get negative A plus B transpose. All right? And what's the next step? Any ideas? Yeah. Yeah, exactly. So I'm going to distribute the transpose. So leave that negative sign out there for now. All right, so that's equal to negative parentheses A transpose plus B transpose. And then now I'm going to distribute the minus sign, negative A transpose minus B transpose. Okay? But what do we know about A, right? A is in my set S, and there's some condition that A must satisfy, right? In particular, A is equal to negative A transpose. So I can rewrite this, right? Negative A transpose is really just A, because it's in my set. Okay? So that's equal to A, and so what is negative B transpose equal to? B. All right, and so wow, what I've shown that negative A plus B transpose is equal to A plus B. So therefore, A plus B is in S, which means it's closed under addition. Any questions? All right. Second condition we have to show is closed under scalar multiplication. Same idea. We're going to take a matrix A and S, but now we need a scalar. So assuming that we're in a real vector space, we're going to take some scalar K, and it's going to be a real number. All right, so now what do we want to show? Well, we want to show... What do we want to show? Yeah. So some constant times A is equal to negative constant times A transpose, right? We want to show that it satisfies my condition. So same idea. I'm going to start with the right and move left. Again, it doesn't really matter. So now I got negative Ka transpose. All right. I'm going to factor out the K because K is a scalar. And if a transpose is a scalar, nothing happens. It's just a scalar. So this is K times negative A transpose. Okay. And then now what? Well, what is negative A transpose? A. All right. So we're done. All right, we show that negative Ka transpose is equal to Ka, and so therefore Ka is an element of my set, and so that's closed under addition as well. All right, so once we showed those two, we're done, and we've shown that this is a subspace of M2R. Any questions? Okay, so let's do another example, and this one you've seen in class, but it's really important, which is why I'm going to do it again. So it's the null space of a matrix A. All right, and I believe Professor McGrath calls this a kernel. Okay, they're the same thing. I prefer null space, but same idea. Kernel is more general. All right. So what is the set notation of a kernel, right? So essentially the definition is S, right, is going to be some vector x in Rn such that Ax is equal to 0, right? So the kernel is all of your x vectors that makes Ax become 0. So if we have A, which is n by n, right, and then you have x, which is n by 1, right, and then you want the 0 vector on the right-hand side, and there's m of these, right? We're taking all the x vectors. That did not work. All right, we're taking all these x vectors, and notice if A is an n by n matrix, x is n by 1, which is why we're in Rn. All right, that's why x is an element of Rn. Okay, and I should write that A is an n by n matrix. Okay, so now let's show closed under addition. Okay. So how are we going to show closed under addition? Well, like before, right? What did we do up here? I took two general elements in my set. Okay, so I'm going to do the same thing. Let's take two general elements in my set. Take x1 and x2 and S. All right, and now I want to show that ax1 plus x2, dang it, ax1 plus x2 is equal to 0. Okay, so how do I do this? Well, I'll distribute. Okay, and then when I distribute, what is ax1? It's 0, right? Because x1 is in S, And every vector in S satisfies AX equals 0. Right? So this is 0. And what is AX2? It's also 0. All right, so then this is equal to 0. So I've shown that x1 plus x2 is equal to 0. And so x1 plus x2 is an element of S. So that's closed under addition. Okay, let's do closed under scalar multiplication. Take x1, or I don't need to call x1. Let's just take x in S and k in R. All right, so I take one element of my set and one scalar. And now I want to show that A times kx is equal to 0, right? Because that's the definition of a null space. So what can I do here? Well, I can just factor out the constant, which is like generally the case. Oops. All right, so that's kax, right? X is in S, so it satisfies the condition up here, and therefore ax is equal to what? 0. So this is equal to k times 0, and so that's equal to 0 as well. So therefore kx is in S, and so we've shown that the null space of a matrix is then a subspace. Any questions? All right. Okay, I'm 5 minutes ahead of last recitation. This is good. So, all right. So that's about it for subspaces. If you're ever asked to show that something is not a subspace, or you think something's not a subspace, you can just come up with a counterexample. All right, that's good enough. You can come up with a counterexample that show it's not closed under addition or not closed under multiplication, or you can just show that the 0 vector is not inside. That's also enough. But if you have to show that something is a subspace, you must run through both steps, and you must show both steps. So, okay. 4.4 is span. All right, so before we get into span, let's do some definitions. The definition here, then, first is going to be linear combination. All right. And it's the following. So all of these definitions are going to start with a set of vectors. All right. So the linear combination of a set of vectors v1, v2 through vk is c1v1 plus c2v2 plus plus ckvk. All right, where c1, c2, all the way to ck are some constants. Okay, so essentially what a linear combination is okay, here are a bunch of vectors, right? And let's just slap some constants in front of all the vectors and just add them all up. All right? So the most important linear combination that we're studying, or that we have studied, right, has been system of equations, right? Because for a system of equations, right, let's say I have the following. Let's say I have 2x1 minus 5x2 is equal to 7. And I have 3x1 plus 4x2 is equal to 5, right? So this is one way to present a system of equations, but Professor McGrath, in the very first lecture, also presented this as a linear combination of vectors, right? So one way I can do it is that I can take out my x1, right? And then I can multiply that by what? 2, 3. All right, and then I'll add x2 multiplied by negative 5, 4, is equal to 7, 5, right? And this right here, this is a linear combination of 2, 3 and negative 5, 4. Okay? And this is how you want to think about literally everything from this section on, is that we're going to present you just a bunch of crap in words, and really it's how do I write it as a linear combination, and what does this linear combination mean in terms of a system of equations? Because everything just ends up being row reduction. All right? So that's going to be linear combination. So now let's define what span is. All right, the span is literally all linear combinations of a set of vectors. V1, V2, through Vk. So the span of a set of vectors are just every single possible linear combination that you can take. All right. So what are some common span problems that you'll see? There are a few of them. So there are a bunch of YouTube videos I have that go through all of these. I'm only going to cover like a handful in recitation just for the sake of time. So the first one is going to be determine the span of V1 and V2. And you get V1 is equal to 1, negative 1, 2. And V2 is equal to 2, negative 1, 3. Okay? And so now, this is a really simple question. Just what is the span of V1 and V2? And so we can write span of V1 and V2 as, all right, what's the definition of span? It's literally right there on the board. Right? What's the definition of span? All linear combinations of a set of vectors. So all we do is say, okay, the span is equal to C1 times this plus C2 times the second vector. That's it. All right, that's the span. All right, the second example now is, okay, does V lie in the span? So does V lie in span V1, V2? Okay. And let V equal 0, 1, negative 1. So what is this problem really asking me? So let's interpret all this new vocab into something we know, which is a system of equations. What is this problem asking me in terms of a system of equations? Yeah.
Is there a solution?
Yeah, exactly. Is there a solution to this system of equations? So in other words, is there a solution to the system, right? C1, 1, negative 1, 2, plus C2, 2, negative 1, 3, equals 0, 1, negative 1. Right? Because if V lies in the span, right? Remember, this is the span of V1, V2, then I can find a C1 and C2 that makes this true. Okay? Is everyone on board with that? Okay? So system, so really, when you ask this question, is there a solution to a system of equations? Okay? And so how do we solve this system of equations? Well, we just put it into a matrix and we row reduce, right? So in this case, what goes in my matrix? Yeah.
The augmented matrix on the left side is the V1 and V2.
Exactly.
And the right side is V.
Yeah, exactly. So on the left-hand side of the augmented matrix are just the two columns that I've written up there. So 1, -1, 2, 2, -1, 3. All right. And then the equal sign still is this straight line. And then on the right-hand side, that's 0, -1, 1. Or 0, 1, -1. Okay, so here's my system. If there's a solution, it's in the span. If there's no solution, it's not in the span. All right? So we reduce 1, 2, 0. Row 2 plus row 1, 0, 1, 1. And then row 3 minus 2 times row 1, 0, -1, -1. Okay? And then we'll reduce again. 1, 2, 0, 0, 1, 1, 0, 0, 0. Is there a solution? Yes. Why is there a solution? Yeah, so the rank of this guy is the same thing as the rank of the entire augmented matrix, right? Remember if there's a solution. So yeah, there's a solution, and really what is the solution? The solution is C2 is equal to 1 and C1 is equal to -2, right? Because this row tells me C2 is equal to 1, right? This is C2 equals 1, and then from there I can get C1 from the top row. Okay, so yeah, there is a system, or there is a solution to this system. Okay. Yes, V lies in span, V1, V2. Any questions? So notice this system of equations, it's kind of changed on us. We're used to seeing, right? We're used to seeing x1 and x2, right? And then we're used to seeing like ax is equal to something. But when you're talking about linear combinations, it's essentially like this is A, this is B, and then you're finding like your x vectors. Your x vector is now like C1 and C2 instead of x1 and x2, but that's just like a name change. All right. Okay, so then another example that you'll see with span is, does a set of vectors span a vector space V? So for example, does 1, 1, 0, 1, 0, 1, 0, 1, 1 span R3? Okay. So notice this is a little bit different because above we're asking, okay, here's just one vector, does it lie in the span? But here, I give you a set of vectors, does this span all of R3? Okay? And so how do we do this? Well, remember, what's the definition of span? All linear combinations. So we should set up all linear combinations. Right? So C1 times 1, 1, 0, C2, 1, 0, 1, plus C3, 0, 1, 1. All right? And to show that something spans an entire vector space, on the right-hand side, what do I need to put? I need to put a general element of that vector space. All right? I need to have something that can describe every element that lies in that vector space. So this must be the general element. Or in our case, it's going to be R3. Right? So what does a general element in R3 look like? X, Y, Z, yeah. That works. Okay, so here we go. X, Y, Z. What do we do? Well, what does this look like? What is this problem really asking? Is there a solution to this system of equations, right? That's all it's asking. That's what every problem is asking for here. So, all right, so now we have a system of equations. All right, and all we want to do is show that there is a solution. All right, once we show that there's a solution, we don't even need to find what the solution is. There just needs to be a solution, okay? All right, so we row reduce 1, 1, 0, x. We'll do row 2 minus row 1, 0, negative 1, 1, y minus x. Row, and then this is 0, 1, 1, z. Okay, and then I'll do row 3 plus row 2, 1, 1, 0, x, 0, negative 1, 1, y minus x, 0, 0, 2, and this is z plus y minus x. Is there a solution to this system of equations? Yes, right? Because why? Well, pivot, pivot, pivot. Okay? Right? Each column has a pivot. The rank of A is equal to the rank of the augmented matrix, right? And so there's going to be a solution for every xyz. So what this shows me is that it doesn't matter what I choose for xyz, there's always a solution, right? Which then means, okay, my vectors span R3. So there's a solution. So there exists a solution for every xyz. All right, there exists a solution for every xyz. Therefore, this guy's 1, 1, 0, 0, 1, 0, 1, 0, 1, 1 spans R3. Okay, any questions? What can go wrong? So it worked here, right? But what goes wrong if, so what happens if this were 0?
Then that defines a specific function.
Yeah, exactly. So if this orange entry were 0, right? Then when will there be a solution to the system? Yeah.
Z plus y minus x is 0.
Yeah, when this guy equals 0, right? And then this would be the plane that the vectors span, all right? So I'm not going to, so McGrath talked about this in class, all right? So I would go back and look at the lecture notes. I also have a video that talks about this case where it spans a certain plane, right? It's one of my YouTube videos. So I'm not going to talk about it here, but that's definitely a case, and that's definitely free game like for the exam, all right? So it wouldn't span R3, but it would span a plane, right? Because z plus y minus x equals 0, that's a plane, which is two-dimensional. Okay, any questions there? That's just a hypothetical. Again, go through your notes, go through my videos online. They'll cover pretty much any case I don't get to here. All right. Okay. Anyways. Let's go back. So that's span. All right. And so that's everything you covered up to yesterday. And so now we're going to jump ahead. For 5, linear independence. All right, so definition of linear independence is the following. Always starts out with a set of vectors, v1, v2, vk, is linearly independent if the only solution and only solution to C1v1 plus C2v2 plus C3v3, etc., CKVK equals 0 is the trivial solution. C1 equals C2 equals CK equals 0. Okay, in other words, i.e., v1 through vk are linearly independent if none of the vectors in the set can be written as a linear combination of the other vectors. All right, so this is just a bunch of vocab right now that makes absolutely no sense. All right, let's take a look at some examples. These will be really easy examples. All right, 1, 1, 0, 1, 2, 3. Are these linearly independent?
Yes.
No, why not?
2 times the first plus the second.
2 times the first plus the second gets you the third, right? Everyone see that? So not linearly independent. 2v1 plus v2 is equal to v3. Okay. What about this? 1, 1, 0, 1. Is that linearly independent? You kind of eyeball it, right? Yeah. Right? Because if you have one vector, you can't get to the other one, right? So, yes. Linearly independent. Oh, also not linearly independent. So, like in is like a negative, and then not is a negative. So this is linearly dependent. Right. Okay, and then finally, if you have like 1, 1, and 2, 2, right, is this linearly independent or not?
Yes.
Actually, no. Why not? Yeah, 2 is 2 times v1, right? So no. This is 2v1 is equal to v2. Okay? So as long as one of them can be written as a linear combination of the others, they're not linearly independent. Okay, so how do you formally do this then? So we're doing a lot of eyeballing here, right? How do you actually formally set this up? So for example, our 1, 2, our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 linearly independent. All right, you can also eyeball this one, but let's actually go through the motions. So are these linearly independent? So what's the definition of linear independence? Well, this thing, right? C1v1 plus C2v2 plus CKvk is equal to 0. Okay? So again, all these questions boil down to the fact that here's a bunch of words. There's some system of equations that we need to set up. All right? And in this case, it's going to be C1 v1 plus C2 v2 plus C3 v3 is equal to the 0 vector. Right? And what must be the condition? What must be true for this to be linearly independent?
C1, C2, C3 is
0. Right, exactly. The only solution is the trivial solution. So C1, C2, C3 can only be 0. All right? So what does that mean? Time to put this in the augmented matrix and solve the system of equations. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the right-hand side is 0, 0, 0, 0, which you really don't have to write, but just put it in there. Okay. Play our favorite row reducing game, except we're going to do some shady row reducing this time. We're going to do R4 minus R3, then R3 minus R2, and R2 minus R1 simultaneously. So if you do row 4 minus row 3, you get 1, 1, 1, 0, right? And then if you do row 3 minus row 2, you get 1, 1, 1, 0, 1, 1, 1, 0, and then 1, 5, 9, 0. Okay. And then we're just going to kill the bottom two rows, and then I'm also going to do row 2 minus row 1. So now I get 1, 5, 9, 0, negative 4, negative 8, 0, 0, 0, 0, 0, 0. Okay? How many solutions are there to the system? Infinite. Why? Yeah, rank is less than the columns, right? Another way we can see it, that's a pivot column, that's a pivot column, this is a free variable, right? So when you have a free variable in a homogeneous system, which is what this is, right? This is a homogeneous system. When you have a free variable, you're going to get infinite solutions. So yeah, you can justify it, rank, and let's call this guy A. Rank A is equal to 2, which is less than the number of columns. So therefore, infinite solutions to, this is really AC equals 0, right? Like, we often call it AX equals 0, but now these are like C's instead of X's, so let's just, change the name up accordingly. They're infinite solutions to AC equals 0 because rank A is less than the number of columns, therefore not linearly independent. All right? Or they're linearly dependent. Again, be careful about what the question's asking. Okay, any questions? Yeah.
In general, when we do the reduction on the test, we have to write out like every
No. You can just do something tilde. So that's for row operations. Yeah, so we'll be able to figure it out, hopefully. Okay, so now what? Now, what are some equivalent definitions of linear independence? All right, so these conditions are all the same thing as being linearly independent, right? The first one we kind of already wrote up there, right? If rank of A, so first of all, make the coefficient matrix, coefficient matrix and system of equations. All right, because now we can talk about that matrix A, right, which is the coefficient matrix. All right, so if rank A is less than the number of columns of A, all right, of A, not the augmented thing, just of A. All right, then, whoops, this has to be equal. So if rank A is equal to the number of columns, then it's linearly independent, right? If it's less than, it's linearly dependent. Okay, the second thing is going to be if A has a trivial null space or kernel, right? Because what does it mean to have a trivial kernel? AX equals 0 only has the trivial solution, right? Which is exactly what we want because we want all these C's to be 0, right? So being linearly independent is the same thing as if A has a trivial null space, right? They're the exact same definition. All right, lastly, if A is square, does anyone see what other condition would make this true? What other condition? Determinant not equal to 0, invertible. All right, same thing. So that A not equal to 0, or, right, so this implies invertibility. Okay, so if any of these are true, they're linearly independent. Your columns are linearly independent. Right? because again, remember, how do we form A? We put all our vectors into columns, right? But also, yeah. Any questions? All right, so there's 3 minutes left. Let me hand out the homework real quick. If you need to leave, if I'm running over, which I'll be like a few minutes over, go ahead and leave. But I'm going to cover bases. Yeah, it's on the yeah. That's what this stuff is all covering.
Is it due on Tuesday?
Yeah, the homework's due on Tuesday. We might do something with the recitation homework to like allow you to turn it on Friday if you're in Wednesday section. No promises yet, but yeah, the homework's going to be due on Tuesday. But all the homework's going to be on the exam anyway, so you should probably do the homework before the exam. All right. Let me get a 4-6, which is bases. All right. Again, I don't want to run too far over either because there's someone after me. So, definition, a set of vectors, big surprise, v1, v2 through vk, is a basis for a vector space V if the following is true. 1, v1, v2 through vk are linearly independent, and 2, the set of vectors spans the vector space. So spans V. Okay? So for example, I claim that, let's see, what should I do? I'm going to claim that 1x and x squared is a basis for P2R. All right, so what is P2R? P2R are the polynomials of degree 2 or less. I believe this is notation he introduced in class as well. And sometimes it's just written P2. All right? So what do I have to do? Well, I have to show, 1, I need to show linearly independent. All right, and how do I do that? Well, I need to show that A, well, first of all, I need to show that C1 times 1 plus C2 times x plus C3 times x squared equals 0 only has the trivial solution. Except 1x and x squared are not vectors. Right? So how does this work? Well, we can think about this in the following way, right? 1 is equal to 1 plus 0x plus 0x squared. Right? Everyone agree with me there? Yeah? X is equal to 0 plus x, 1x plus 0x squared. And x squared is equal to 0 plus 0x plus 1x squared, right? So what I can do is that I can create vectors where the first entry is going to be 1, the second entry is going to be x, and the third entry is going to be x squared. Right? And then I just put the coefficient in front of them. Right? So for example, for 1, it's going to be 1, 0, 0, because it's 1 plus 0x plus 0x squared. Right? And then plus C2, and then now what to do for x? Well, this is going to be 0, 1, 0. Right? Because it's 0 plus 1x plus 0x squared plus C3, 0, 0, 1. All right? and then 0 vector is just the 0 vector. Okay, system of equations, solve it, right? We put this into a system, you actually get 1, 1, 1, 0, 0, 0. Right? Are they linearly independent? Yeah, right? Pivot, pivot, pivot. So this is linearly independent. 2, spans. All right. We had an example where I said this is how you show something spans a vector space, right? So how do we show that something spans a vector space? Well, if we go all the way back up here, right? Does a set of vectors span a vector space? Well, you have your set of vectors, and then you need to come up with the general element of that vector space, right? So here's your set of vectors. Well, here's my set of vectors right now. It's 1x and x squared. So now I have c1 times 1 plus c2 times x plus c3 times x squared is equal to, now I need a general element of P2. What does a general polynomial of degree 2 look like, or less?
A0 plus A1x plus A2.
Yeah. So you can have however you want to denote it. I'll do it ax squared plus bx plus c. All right, but again, we're running the same problem, right? What does 1x and x squared mean? Like, these aren't vectors. We can't row reduce 1x and x squared. So we're going to do the same thing. We're going to write it out as these vectors, right? 1, 0, 0 plus c2, 0, 1, 0 plus c3, 0, 0, 1. But now, what's my right-hand side going to be? Not ABC. Be careful. CBA, right? Because I defined the constant to be in the first entry. Okay, CBA. What happens? Well, set up your system of equations, and what are we trying to ask? We're trying to ask, is there a solution, right? That's it. That's all we care about. Is there a solution? So if we go up, that's exactly what we asked up here. Can't find it, right? Yeah, is there a solution? And yes, there exists a solution, right? Here, there exists a solution. So, exists a solution for every CBA, or not CBA, but for every ax squared plus bx plus c in P2. So therefore it spans. And so now we show that it spans. We show that it's linearly independent. So therefore a basis. All right? And so you must show both for it to be a basis. It has to satisfy both conditions. So there's something else. There's dimension, and there's a theorem that makes doing this a lot easier. It's fine. We won't talk about those. Hopefully we'll get to those at like a review session or something. But this is it. This should be everything you need to do the homework and everything that's on the exam for next week. So, yeah, I'll see you guys next week. Again, there's going to be an email sent out with like a bunch of logistics about the exam, review sessions, practice problems, etc., etc. It's going to be in that email, okay? So, yeah.
Are there any problems that like involve us knowing that formula for like linear fitting?
No, least squares is not on the exam. Yeah. Yeah, least squares, that's the one thing he told me explicitly not on the exam. Yeah, you want to head downstairs?
Wait, yeah, because I haven't done calculators. Do we get to make a cheat sheet?
No cheat sheet for this. Yeah, so I thought we were gonna post solutions yesterday, but we didn't. So one of the review sessions is gonna be